Okay. Hello, hello, class, and hello, YouTube. And let's. Everybody ready to get going? Just say yes. Okay. A lot of yeses over there. So let's get back. Let's pick up where we left last time. Okay. So last time I think we very quickly introduced the Hamming 7 code, and things were a little nuts last week anyway. So I'm just going to do that maybe like the last 5 or 10 minutes again, maybe slower. So last time we introduced the Hamming 7 code. So H7, the Hamming 7 code, is the null space of the parity check matrix at H7, sort of capital H7 as opposed to script H7. And so, oh yeah, and so the key point, oops, this is not, so the key point of H7, that's sort of essentially the definition of capital H7, is that the ith column of capital H7, the parity check matrix of the Hamming 7 code, is the binary digits of I, except written upside down. So here goes. Let's see if this works. So if I look, for example, at column 5, oh, well, column 5 is not a good column to illustrate my point here. My bad, but okay. So this is the binary digits of 5 upside down. Except 5 is 5. Except the number 5 has a palindromic binary digits. So that was a poor choice of column to illustrate this. Let's try this. So this column is column 3, and that column is the. Oops, let me move the chat window over. That window is the binary digits of 3, i.e. 0, 1, 1, upside down, because they're written, instead of writing 0, 1, 1 as you might normally, going from top to bottom, they're going from bottom to top, 0, 1, 1. So are there any questions? So actually, let me ask: is everybody okay with how to remember this matrix, this magic matrix, capital H7? So Than asks, the binary digits are the weights of the weights of what? Yeah, Than, can you turn on your mic and sort of say what the weights of
Oh yeah, like for 0, 1, 1, right? Like
uh-huh.
the weight of the binary is 2 to the power 0 and 2 to the power 1. Is that where you're getting your 3?
Yes, that's right.
Okay.
That's right. Yes, let me do that for 6. So for 6, right? So here's a quick review of binary. Excellent question, Sam. Thank you very much. Let me do 6 here. So why is this? Why is this? Why is it that 6 is equal to 1, 1, 0 in binary? Because that's equal to 1 times 2 to the 2 squared plus 1 times 2 to the 1 plus 0 times 2 to the 0. Yes. So right, exactly, Fan. In that sense, thank you. The binary digits of a number are the weights that you give to the powers of 2 to add up to that number. So Fan, did that answer your question?
Yes. Thank you.
Yeah, thank you. That was an excellent question. Okay, so now I hope it's not mysterious as to where as to how you might remember the columns of H7. It might still be mysterious as to why on earth this should work, but okay, or this should be useful at all. But we'll actually try to clear up that mystery a bit today. Any other questions about that matrix, that magic matrix, capital H7? Okay, so So the idea when you encode and decode data in the Hamming 7 scheme, the idea is that you're trying to transmit four data bits, 4 message bits, and you copy those 4 message bits into bits 3, 5, 6, and 7, and then the other bits, x1, x2, and x4 are governed by these equations: x1 equals x3 plus x5 plus x7, and so on. I should actually talk about, if you look at the top row of capital H7, the top row of capital H7 is 1 0 1 0 1 0 1. So yeah, so where does this come from? That's because that equation comes from the fact that the top row of H sub 7 is 1 0 1 0 1, which gives the equation, oops, that's not what I wanted to do, hang on. Still working out a few bugs in this, and working out in my new piece of software, which gives the equation x1 plus x3 plus x5 plus x7 equals 0. So remember, because remember, because the Hamming 7 code is the null space of this matrix, that means exactly that you think of each of the when you use this matrix, the parity check matrix, to define the Hamming 7 code, each of these rows of H7 gives you an equation, and the top equation says exactly that H1 plus x1 plus x3 plus x5 plus x7 equals 0, and then because plus 1 equals minus 1 mod 2, we get that x1 is equal to x3 plus x5 equals plus x7. I mean, that's actually the great thing about doing everything mod 2, is that you cannot make any sign errors, because plus is the same thing as minus. Yay! It's been everyone's dream, right? Okay. Anyway, so and similarly, you can read the other rows of H7 in a similar way, and get that that tells you what x2 and x4 have to be after you've chosen x3, x5, x6, and x7. Okay, so are there any questions? Yeah. Let me know if you have any questions. Just type in the chat box. In any case, so Xavier chooses the bits x3, x5. Whoa, that was not what I wanted to do. Chooses the bits x3, x5, x6, and x7, and then determines the other bits x1, x2, and x4 by equation. Xavier transmits capital X, which is all 7 bits. That's all. Why is that there? Oh my goodness, all 7 bits. I do not know why this giant keyboard suddenly appeared. All right, that transmits all 7 bits. Yolanda receives some 7 bits, but maybe not the ones that Xavier transmitted. And then Yolanda then decodes Y by computing the syndrome, and then hopefully correcting y to y prime, and then reading the message m prime off of bits 3, 5, 6, and 7 of y prime. And I think, as we had last time, I think it's better to do an example. Probably that didn't make a whole lot of sense, especially if you. Let's see. So Ryusei asked, "Is the top row the binary sum of those x's?" Yes, it's all. Everything is in mod 2. So Ryusei asked, if we're looking at are we looking at binary sums? And the answer is yes. It's because everything is in the vector space f2 to the 7, and so all calculations are done mod 2. So Ryusei, did that answer your question? Actually, let me write something on while I'm waiting to see if I answer your question. let me write something on the slide here. This is all, whoa, what the heck? What was that? Mod. Mod 2. Ryusei, can you want to turn your mic on and sort of articulate your question a little more? Or did I answer your question? Ryusei, you still there? Uh-oh. Let me test to see if I'm still recording. Can everybody just say yes if you can still hear me? Okay. Oh yeah, Ryusei, your mic. I guess maybe yes, maybe your mic is broken. So can you type out whether that was okay? So did I answer your question? Yes, each of the x's represents one bit. That's right. Bit numbers 1, 3, 5, and 7. And so the top row of H7 being 1, 0, 1, 0, 1, 0, 1 says that when you transmit a code word, then that code word has to satisfy the equation x1 plus x3 plus x5 plus x7 equals 0, everything done mod 2. Does that make some sense?
Can I also ask a question?
Oh yeah, your mic is working again now. Hey, yeah, sure. Oh no, this is Than, right?
Yeah. So can you explain about the G7 that you wrote down, like right after H7?
Oh yeah, what was that? Right. So let me talk about where this comes from. We won't use it very much, but let me talk about where it comes from. If we solve H7x, I better write that in H7x equals 0. Using our usual methods, this is the basis we get for the null space of H7. Oh,
Okay.
or rather, the columns of G7 form the basis we would get for the sort of standard basis that we get for the null space of H7. Yeah. So if you just do chapter 5, the point is if you just do chapter 5 on this set of equations, which is already in reduced row echelon form, this is exactly what you get. So, Than, that answer your question?
Yes. Thank you.
Yeah. Excellent. Thank you so much for that question. Okay. So again, I think one thing to do, if this all seems a little mysterious, I think one thing maybe the first thing to do is to try the problems where you just do one, where you actually sort of work through it, and then sort of come back to like where did this all come from. Okay, so let's actually try to do a problem. So can somebody give me 4 message bits? So this is what Xavier wants to send. Just somebody type in four. Okay. Alexis wins, I guess. 1, 1, 0, 1. All right. So suppose Xavier is sending the wants to send the message 1, 1, 0, 1. Okay. So then there will be 7 bits here. Let's see. 1, 2, 3, 4, 5, 6, 7. All right. And so we said that that the message bits get copied into bits 3, 5, 6, and 7. All right. So remember that was the first step of that of this algorithm, you copy the 4 data bits into bits 3, 5, 6, and 7. So every case so far. Any questions so far? Okay. Now, let me switch colors here. So here, each of these equations tells you what the other bits 1, 2, and 4 has to be. So bit number 1 has to be the sum of bits 3, 5, and 7. 3. Where's my curve? Well. Uh-oh. All right. Well. Anyway, there's my cursor. All right. So bit number 1 is the sum of 3, 5, and 7. So that's an odd number 1, so we get a sum of 1. Bit number 2 is the sum of bits numbers 3, 6, and 7. 3, 6, and 7. Bits numbers 3, 6, and 7. Well, that's 1 plus 0 plus 1 is 0. And bit number 4 is equal to the sum of 5, 6, and 7. And so again, there's my cursor. 1 plus 5 plus 6, 1 plus 0 plus 1 is 0. And so, right. So this is going to be our vector x that is transmitted, that Xavier transmits. So M is your message, and x is what you transmit. What you transmit. So does everybody see how I got x from M? Okay. No, at least no questions, no open questions so far. So then what happens is, what usually happens is, at least to make this interesting, there'll be some, so that's all on the Xavier side of things. Now we get to Yolanda, our faithful receiver. And usually what will happen, I mean, the reason that error correcting codes are interesting is that usually it will happen, and we always imagine that there will be some sort of error happening in the middle. And so let's change one of those bits. Somebody who hasn't sort of chosen anything so far today, pick a bit to be flipped. It's kind of like a magic trick, I guess. Oh, except there's no bit 0. The bits are 1 through 7. Yeah, we're reserving the name 0 for something else coming up soon. Bit number 3. Okay, so that means bit 1 is the same, bit 2 is the same, bit 3, something's gone wrong. What's a good color for something going wrong? I don't know. Purple. So bit number 3 gets messed up, and then the other bits are transmitted as intended. So that purple bit is where we had an error. Oh, lavender, actually. So there's our error creeping in. Okay, so now, oh yes. Oh no, is this sort of okay? So now I'm gonna have to copy this over here. So 130 is 101, 101. So now we have it here, y equals 1 3 zeros 3 zeros 101. Okay, so I'm just copying over this y down here, just because it doesn't really it just doesn't fit in the screen. All right, so now what we're going to compute is we're going to compute the syndrome S. Remember, the syndrome is going to be H7 times Y. right? So what we do is we actually do a matrix multiplication. Remember how I said that row vector multiplication is actually it's the form of multiplication you may have spent the least time thinking about. It's actually our most important. So here we are. This is all going to boil down to a bunch of row vector multiplications. Doesn't want to seem to. Okay, let's try that again. All right. So there we go. Okay, so and remember the principle, the way to do this, I think the way that at least the way that I like to do, you could just sort of sit here and now and do those multiplications, but the way I like to do this is that I want to think is that row vector multiplication is a linear combination of columns with coefficients coming from the row, with coefficients coming from the vector. Sorry, it's not row vector. Sorry, I keep saying row vector multiplication. It's actually matrix vector multiplication. Is a linear combination of the columns of the matrix with coefficients coming from the vector. So so this multiplication S equals H7 times Y is really just the sum of columns. Well, Y itself has a 1 in positions 1, 5, and 7. So this is column 1 plus column 5 plus column 7, which is equal to, well, if I add columns 1, 5, and 7, here's column 1, here's column 5, and here's column 7. What you'll see is that you get a 1, you get 1, 1, 0 equals 1, 1, 0, which magically is which is, hello? I thought I heard something weird happen there. This is column 3. And so once that happens, then the rest of the computation isn't so hard, and I'll just sort of leave that part out. So Yolanda corrects bit 3 to 1, and from remember the purple error made bit 3 0, and it should actually be 1. So and this tells you that because you just read this as column 3, Yolanda will now because it's the binary digits of 3 upside down. So Yolanda will now correct bit 3 to a 1, and reads off. Well, once this is corrected, she can just read off the intended message. Okay, so are there any questions about all this? I wonder if there's some way to make this smaller. View. Oh, look, that was interesting. Huh. This is like none of the tools I actually want. So anyway, so are there any questions? Well, so at least I can at least temporarily show you what the whole thing looks like. So any questions? Are there any questions about this entire process of encoding and then an error and then looking at the syndrome and then decoding? Are there any questions about that so far? Or if not, just say good and then we'll move on.
Can I ask a question?
Sure. Fan, right?
Yeah. But what if your error is a 0, like on bit 2?
That's a good question. It will still work. I mean, the short answer is it will still work, and we have to prove why, right? So, but it will still work.
Okay.
So that's good, Fan. That is excellent. I congratulate you, yay, Fan, because you were skeptical. You're like, how could this can't possibly work all the time? But this is why we have proof, because in a minute we're going to prove algebraically. I mean, on the one hand, you should just try it yourself. Just you just even take this example, mess up bit number 2, and see what happens. Um, what will actually happen, what we'll actually show in a minute, we'll explain algebraically why even a 0 to 1 error will also be corrected in exactly the same way. So so hang tight, okay?
Yep. Thank you.
All right. Any other questions? Or is everybody good? Just type good if you're good.
I have a question.
Okay, go for it.
So, if we would have chosen any other bit, the linear combination would be different, right?
Correct.
Okay.
You'd have a different linear combination of columns.
Okay. Thank you.
Welcome. Great. Any other questions? Okay. Oh, what if there are no errors? If there are no errors, Ryusei asks, what if there are no errors? Well, if there are no errors, then because x is in the null space of H7, yeah, suppose, so if you just look at what happens if you just pop in x, if you type H7 times x, H7 times x is equal to 0. That's right. Ryusei said, oh, right, it's 0, right, because that's the whole point, that x is in the null space of H7. And you can actually check that the column 1 plus column 3 plus column 5 plus column 7 is in fact 0. Magically. Okay, not so magically. If there, Ishan asked, what if there are multiple errors? Well, then you're out of luck, because you can try it. I mean, it's sort of interesting to try. If you have multiple errors, what will happen is that you will, if you have more than one, let me say if you have exactly 2 errors. If you have exactly 2 errors, what will happen is that you'll get a correction, but it'll correct your sort of received code word to the wrong code word. So because there's and that's actually something we'll talk about today. There's sort of by nature, it has to be some limit on the amount of error correction that any of these schemes can have, and we'll talk about one way of computing how good an error correction scheme could possibly be. Excellent question, right? Yeah, if there are multiple errors, it won't work, because the Hamming 7 scheme corrects exactly 1 error. Okay, great questions, everybody. Any other questions? Okay, let's see. No. How do I stop full screen? Oh no. Oh, bummer. Where's like line annotations? Well, this was worth a shot. Extras, favorites, file, help, view. Here we go. Exit full screen. Fantastic. There we go. Why will you not actually exit the full screen? Oh my God. Okay. Well, we're gonna go in full screen for a while then. My bad. Okay. So this isn't actually. I mean, this isn't actually so bad. Going to full screen. Oh, why there's a big X? Why is there a big X there? Okay. Never mind why there's a big X there. I do not understand why there's a big X there. Eraser. Oh my God, here we go. Ah, there we go, fantastic. It just took a while, that's all. Oops. Undo, there we go. So let me more carefully erase this. All right. Hey, everybody out there in YouTube land, just ignore those X's that showed up. I have no idea why they're there. I'm a middle-aged man. What do you want? Oh yeah. Okay. Here's proof. Proof is good. Okay, so let's talk about the proof while that decoding works. All right, let me ignore the previous ignominious lack of computer skills, and let's go back to something I know how to do somewhat, which is proof. Okay, so theorem. So and the point of this theorem, let me try to redeem myself a little bit here by typing something coherent here. The point of this theorem is that Hamming 7 corrects. Oops. There we go. Corrects one error. As Ishant points out, was asking, not more than one error. So remember, this is the sudden intrusion of this little bit of algebra here is that this is our algebraic model. Of making one error. So I think Fan was asking earlier, well, what happens if you switch that bit 2 instead of from a 1 to a 0 like we've been doing, instead to a 0 to a 1? And the answer is the lovely thing about this algebraic model of errors is that switching a 0 to a 1 is exactly the same algebraic operation as switching a 1 to a 0, because adding 1 in bit I switches 0 to 1 and switches 1 to 0. So Than, that was actually really the sort of detailed answer to your question. Oops, that was not what I wanted. There we go. Than, yes, thank you for the suggestion to the old man. Escape eventually worked, but I think something else captured it. Anyway, so all right, so sorry. So Than, as I was answering your earlier question, the point is that we have actually a uniform algebraic model of flipping 0 to 1 or flipping 1 to 0. It's you add on the vector e sub I. So remember e sub I, and let me remind you what e sub I is. Oops, that's not what I want to do. I want to do this. E sub I is a vector with 1 in coordinate number I, 0 elsewhere. And now let me fix that box. All right, so yeah. Anyway, so here's the proof. Proof is, since the transmitted code word X is in H7, is in Hamming 7, which is the null space of capital H7, by definition, as we were just saying, talking about with Ryusei, capital H7 times X equals 0. Therefore, the syndrome, remember, so this is the actually, it's good to give this a name. The syndrome S is equal to, by definition, remember, which we got by multiplying H7, the parity check matrix, times the received word Y, is equal to H7 times parens X plus E sub I. Matrix multiplication is distributive. Oh my God, I bet you never thought that'd be useful, but yes, matrix multiplication is distributive. If I can actually remember. Matrix multiplication is distributive. I should never thought that'd be useful, but there it is. So H7 times X plus EI is equal to H7 times X plus H7 times EI. Well, H7X is 0, and so we get the syndrome is equal to H7 times EI, which is the ith column of H7. However, by construction, the way we build that H7, that is the matrix whose ith column is the binary digits of I, and bada boom, bada bing, we are done. Yay! I think that deserves a smiley face. I think that's a pretty cool thing. So yes, there you go, Than. I'm not sure how convincing that is, but that really is a proof that no matter where we make the error, and whether we change from 0 to 1 or 1 to 0, the same thing will happen. And magically, the syndrome will tell us in which position the error occurred. Ha! Okay, so are there any questions about this theorem or its proof? Or shall we move on? Shall we move on? Say yes if you everybody say yes. Okay. And actually, as some of you have probably figured out, one nice thing about this is that you can actually watch all this again on the YouTube. Fantastic. Okay, so here's a very similar thing, and I think I'm just in lecture today, in sort of online lecture today, and on YouTube. All I'm going to do is I'm just going to sort of introduce it, and then I'll leave it to you guys to play with on the problem sets. So so the Hamming code H8 is the null space of this matrix. And what is this matrix? Well, all it is let me see if I can draw that. I'm going to try to use the mouse to draw this a little more carefully. So if I block off this part here, whoa, there we go. So H7 is what's down here. So if I just look at if I delete the first row and first column of H8, I get H7. And so to get H8, what I did is I took H7, the parity check matrix for the Hamming 7 code, and I add a row of all ones at the top, and I add some zeros in the front. So in order to be consistent with the Hamming 7 code, I think I can't remember who said this before. I think it was somebody was talking about bit 0. Well, we reserve bit. We sort of again number the bits 1 through these bits over here corresponding to these columns as 1 through 7, and we number our new bit 0. So we're going to write an arbitrary element of the Hamming 8 code as using coordinates x0 through x7 as opposed to x1 through x8. And so here are the facts about Hamming 8. Anyway, so this is just a very quick introduction. You know, all you really need to know in terms of the homework is that this is going to be a binary linear code with this parity check matrix. And so, and the fact that you're going to sort of explain on the homework, look into and explain on the homework, is that the Hamming 8 code, H8, is the Hamming 7 code, H7, extended by a parity check bit, x sub 0. And sort of you get the same. What do I mean by what I mean extended by? That means that we're actually using the same. We actually have really exactly the same code words as Hamming 7, but x0 is an extra, is a parity bit added to each one. Yeah, so that's what I mean by extended by a parity check bit. Parity, oops, let's see, check bit added to each one. There we go. And as you'll see on the homework, the Hamming 8 code corrects one error, just like H7, the Hamming 7 code does, but also detects 2 errors. Because one thing that happens with the Hamming 7 code, as we'll see, but as I was answering Ishan's question earlier, if you make 2 errors, you can't even really detect that. It'll sort of correct it the wrong way. And the proof is in your homework. All right, so before we move on to some more kind of an abstract version of all this, Are there any questions about Hamming 8 and the facts of Hamming 8? All right, I'll wait 10 seconds, see if anybody has any questions, and then we'll do a little theory. Okay, so moving on. All right, and again, if you really have questions that you're sort of holding back, I mean, I think it will probably help to just do some of the homework. Especially try that homework for 6.3. Try the one, and you can really start. It's probably a good place to start is the ones where you do something concrete, where you actually do the same thing that I was doing over here, where you encode and decode. Those are pretty fun, actually, and it's really kind of remarkable that it works. And then maybe get to the sort of the explanation things. Hello, everybody there? Did everybody else hear that buzzing noise? Or is it just me that I hear? Yeah, okay. Well, you're all still there. Very good. All right, anyway, so let's so in order to talk about effectiveness of codes in general, we need to do a little bit more abstraction. So here goes. So so first of all, this is a piece of notation. So this is just so notation. This is just a piece of notation. What do I mean when I say a bracket NKD binary code? So an NKD binary linear code is a binary linear code such that has length n. So in other words, this is so what does that mean to have it for a code to have length n? It means that this is C is a subspace of f2 to the n. That is all the vectors in C have n entries, have n coordinates. The dimension of C equals hey. Well, we know what that means. And then the D is sort of a new thing. D is the smallest number of non-zero coordinates appearing in a non-zero code word of C. And so yeah. So n well, this is the new element here. This minimum distance D. So n is the length. N is the length. K is the dimension of the code, and those are things that we know. And the new thing is this minimum distance D. But yeah, so we'll explore that momentarily, a bit more momentarily. So D is the smallest number. Again, D is the smallest number of non-zero coordinates appearing in a non-zero code word of C, and that's the minimum distance. So it turns out, here's a bit of foreshadowing. It turns out that good at having a large minimum distance is the same as correcting lots of errors. So yeah, so if you want to sum up everything that happens in section, this is now in section 6.4. So we'll just do just a bit from section 6.4 here. If you want to sum up section 6.4 in a sentence, it's that having a large minimum distance is the same as correcting lots of errors. Okay, so let's give some examples of this sort of NKD classification for different codes. So the parity check code of length n plus 1. Remember the way that's defined is that we have data bits x1 through xn and a parity check bit x0. Is this ever going to come back? This is never going to come back. That's fine. Parity check bit x sub 0. I don't know why I was unable to get to that box, but there it is. All right, so that's what happens in the parity check code of length n plus 1. So in that case, well, the length is the length. It's so the length is n plus 1. Is n plus 1 because the length is the length. The dimension is n, because the data bits are chosen freely. Now let me see if I can get this box to work. Or I could not get it to work before, because the data bits are chosen freely. And any non-zero code word has an even number of ones. So remember, the whole point of the parity check code is that you take your data bits, however many ones there are in the data bits, and then and if there's an odd number of ones, you add a 1 for the parity check bit, and that so any non-zero code word would have an even number of ones. So the minimum distance is 2 from 1 1 0 0 0 0, however many zeros that is. So the parity check code of length n plus 1 is going to be a, no, that's not what I want to do. I like that the way it was. And now I'm going to move this here. Move this here. No, move this here. Here. This is going to be a n plus 1 comma n comma 2 code. So when I say so this is a code of length n plus 1, dimension n, and minimum distance 2. All right, so that's what happens with the parity check code of length n plus 1. For the repetition code of length n, so the length is n, okay, just like it says. So the length is n, like it says by definition. Oh yeah, let me remind you what the repetition code of length n is. So this is the code. This is the code that has exactly the words in it. So this is length 8, I guess, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. For length 9. So remember, the repetition code of length n, which we saw before, is the code that has exactly two code words in it. Oh, okay. Hang on, John V. I see your question. Let me hang on a second. Let me come back to it. So the repetition code of length n has is the binary linear code with exactly 2 words in it: the all zeros word and the all ones word. And this has here's one of length 9. Okay, so John V, can you turn on your mic and sort of elaborate on your question? Like, how'd you get the minimum distance 2?
Yeah, so in the previous question, like, how did you decide the distances 2?
Okay, so let me elaborate on that. I think I said it out loud, but let me elaborate it. Let me elaborate that on to a bit more. That is, we can't transmit 0, 1, say 1, 2, 3, 4, 5, because that doesn't we never transmit, because that word doesn't satisfy x0 plus x1 summed up through xn equals 0. So there isn't a sentence, but I'll try to say a bit more about that. All right, so that is we never, or Xavier never transmits that, because remember, so when we use the parity check code, we have some initial number of data bits, right? So that one with 5 zeros, that's the message we actually want to send. Remember? So John B, you with me so far?
Yeah, that makes sense.
Yeah, and then you add on a parity check bit to make sure that the number of ones that appears is even. And so yeah, so you can never transmit something of distance of length of distance 1, and so the minimum distance is 2. Okay, so you're good?
Okay, gotcha. Yeah.
Thank you. Excellent question. Anyway, for going back to the repetition code, that's a code of length n. So that's our length. The dimension of the code is 1 because the all ones vector is a basis. And the minimum distance is So somebody want to give a guess as to what the minimum distance of is in the repetition code of length n? All right, thank you, Alexis. It's n. That's right. It's n because the all ones vector is the only non-zero code word. So the stats on this code. This is an N1N code. All right. Excuse me. So now the computation. So for the Hamming codes, Hamming 7 and Hamming 8, these computations are not as straightforward, especially the minimum distance. So, oops, keep doing that. Are not nuts. Do this again. Try this. This. There we go. There we go. Not as straightforward. Especially these minimum distance computations. Oh, actually, let me start over. Sorry, my bad. Okay, so H7 has length. We saw before has length 7 and dimension 4. And how do we know that H7 is dimension 4? Well, I just sort of asserted it to you, but we know that the Hamming 7 has dimension 4 because of exactly what's happening over here. So let me put that in green. So there's 4 vectors in a basis for Hamming 7, so it has dimension 4. It's a 4-dimensional subspace of f2 to the 7. And so so H7 has length 7, dimension 4. Hamming 8, I guess I should say Hamming 7 has length 7, dimension 4. Hamming 8 has length 8 and dimension 4, as it happens. You can calculate in a very similar way. The minimum distance is not easy to calculate. So, of course, if I have anything not easy to calculate, what am I going to do? I'm going to have you doing the homework, of course. So on the homework, you do this by brute force. List all the non-zero code words and check. And I have to say, well, it's okay. It's maybe mildly tedious, but it's not that bad. And I have to say, I had a student express skepticism. He was a very good student, actually. I think last time, I can't remember if it was the last time I taught this or the time before. But he said, well, there must be an easier way to do it. And then he looked it up, and it actually turns out that that calculating the minimum distance of a binary linear code is it's what they call an NP-hard problem. I guess if you're not as sort of, well, if you're not into complexity theory like I am, I don't know that much about complexity theory. NP might just sort of might as well stand for not possible. It's a computationally very difficult problem, and so so at least so the brute force is going to be mildly annoying, but it's okay. Anyway, oh yeah, but it turns out to be 3 for Hamming 7, and 4 for Hamming 8. So these are 743 and 844 codes. So those are the stats. Okay, so okay, 15 minutes left. So are there any quick questions before we do a little geometry? I know, where did that come from? But so everybody ready for a little geometry, or at least ready as you're ever going to be? Say yes, or ask questions if you have questions. Yes, a little uncertainty here. Anyway, you can always rewind the tape. This is the beauty of this.
I don't understand the part where you wrote dimension 4 for Hamming 7 and Hamming 8.
Okay. So for Hamming edge, I'll say calculation omitted. But let me. I actually did the calculation for Hamming 7. So let me go back and I underline that. So remember how we said, okay, and it's back here. Remember we have this H7 and G7? Dan, does that sound familiar?
Yes.
Well, in fact, I think you actually asked about this. Like you asked, where did this G7, what was that G7 all about? And the idea was that, so the Hamming 7 code is the null space of capital H7. And so to find a basis for that null space, we solve the equations H7x equals 0 using our usual methods. So remember,
got it.
And you're good?
Yeah.
Yeah, and
Right.
as dimension 4 goes 1, 2, 3, 4.
Right.
Yeah, there's nothing like deeper than that. It's just, well, we got 4 vectors and there it is.
Oh, okay. Got it. Thank you.
Welcome. Thank you. Good question. Yeah, so that's and you can do something, and because I guess let me at least stop by here, because this is also this is not in reduced row echelon form, but it's at least in row echelon form. Here you can sort of do the same computation and get a basis for Hamming 8 that has 4 vectors in it. Or actually, you could just use rank nullity. Rank nullity gives the same answer. Yes, and actually, I might have just done the homework for you, but that's okay. It's a crazy time. Okay, so any other objections before we move on back to geometry? Okay, so let's talk about Hamming distance. Okay, so the Hamming so if x and y are in f2 to the n, they're sort of words of code words of not necessarily code words, but words of length n. Then the Hamming distance between x and y is the number of coordinates in which x and y are different, which is equal to the number of non-zero coordinates in x minus y, which is also equal to the number of coordinate changes needed to get from x to y. And the Hamming weight of x is d of x0, which is the number of non-zero coordinates in x. Okay, so let me, that might have been a little fast. Let's talk about, so let's do a concrete example. X equals 1, 0, 1, 0, 1, 0, okay. And let y be, make a little more space here. Y is 1, 1, 0, 0, 1. Oh, actually, you guys give me some. Can somebody type in a random bit string of length 8? In the chat, or should I just do it? Oh, there's one. Okay, that was good. 1, 1, 0, 0, 1, 0, 0, 1. Okay. All right. So which bits need to be of x need to be changed to get to y? Well, actually, let me. We're a little short on time, so let me just do this. I know. So I hope everybody is sort of looking at this. So bit number 2 has to be changed to get to y, to get from x to y. No, don't do something weird. Why did you do something weird? Okay. Bit number 2 has to be changed. Bit number 3 has to be changed. 4 and 5 are okay. 6 is okay. And 7 and 8 have to be changed. So so bits 2, 3, 7, and 8 have to be changed to get from X to Y. And so the point is, that's the point I want. Okay, no, that's fine. There. All right, so the point is that we need to change 4 bits of X to get to Y. So the distance between X and Y is 4. So that's what the Hamming distance is. It's the number of coordinates where they're different, which is exactly the same as the number of coordinate changes to get from X to Y. So is everybody good so far? Yes, some of you are catching on that. If you don't say yes, I will just sit here uncomfortably. Because what else do we have to do? Thanks. Thank you for your support. All right, so that's what the Hamming distance is. So a Hamming path is sort of similar. Here's a sort of way of thinking about this geometrically. So geometrically, we can think of you have to be pretty geometric to think for this to be helpful, but it's kind of helpful. Geometrically, f2 to the n is an n-dimensional cube. Whoa! I can hear it. That's the sound of your mind. The sound of your mind being blown is an n-dimensional cube. Whoa! Right. So this is f. So what we have over here on the left is a little picture of f2 to the 3. And so a Hamming path of length k and f2 to the 3, f2 to the n is a sequence where each step changes exactly one coordinate. So like 0, 0, 0 changes the first coordinate to get to 1, changes the third coordinate to get to 101, and changes the second coordinate to get to 111. So yeah, so a Hamming path of length k is a path of length k in the stepping along the graph of the n-dimensional cube, if you like. And the theorem, the sort of the reason why I bring up this idea of a Hamming path is that the Hamming distance is precisely the length of the shortest Hamming path from X to Y. It's because, and the reason why that is true is because each step of a Hamming path, there we go, each step of a Hamming path changes exactly one coordinate. Right, because each step of a Hamming path changes exactly one coordinate, then the length of the shortest path from X to Y is exactly the number of coordinate changes that you need to make to get from X to Y. All right, so the nice thing about the point of this is that, so this is helpful because we can think of Hamming distance in terms of paths, using paths. Okay, so all right, so just quickly here. Yes, so Ishan asks, which also means that you don't change the same bit twice. Yes, if you're taking a most efficient, a shortest path possible, which is important to notice that the word shortest here. It's important to, because we're using a shortest path. Yes, then if you're going from X to Y, you don't want to change the same bit twice, because if you did that, you can make a shorter path. Okay, so one sort of notable thing about the Hamming distance is that it's a metric, and sort of this is sort of the official definition of what a distance function is for mathematicians. It's a way of defining. You have all these sort of more very natural functions of distances. Distances are always non-negative. The only point that's distance 0 from you is yourself, and all distances are two ways. It's the same distance to get from. It's the same distance from Fremont to San Jose as it is from San Jose to Fremont. The interesting one here is the triangle inequality, which is so let me just draw a little picture here: x and y and z. So what does the triangle inequality say? The triangle inequality says that if you're trying to get from x to z, there's no shortcuts through an extra destination y. So the triangle inequality says that there's no shortcut through the extra destination y. It's just sort of like if you're trying to get from Fremont to San Jose, you can't make your trip shorter by deciding to go through Oakland for some reason. Okay, so and the proof that Hamming distance is a metric, it satisfies the triangle inequality. That's sort of the interesting part, is that it's calculated by Hamming paths. So if you're trying to get from, if somehow this is your shortest possible path from x to z, that's your distance from x to z. Well, if you go up here, actually, let me change colors for that. So if I take some alternate route, oops. Oh no, and now I've erased my letters. By the time we get through this, I'll be really good at this, and then I won't need it anymore. Yes, exactly. So if I take this alternate green route from x to y to z, these paths can't add up to something shorter. Add up to something shorter, because otherwise the red path would no longer be the shortest path from x to z. So yeah, that's exactly what the triangle inequality says. And so any kind of distance that you can think of in terms of path, the idea is that any distance that you can think of in terms of paths has to satisfy the triangle inequality. Okay, and that's the sort of interesting point here. All right, sort of very quickly. Shoot. Okay, so let me just very briefly talk about nearest neighbor error correction, and then I think we'll talk about, this is sort of worth savoring a little bit, this proof that above minimum weight and error correction. So I'll just stop. I'll just talk a little bit about nearest neighbor error correction. So the nearest neighbor error correction method in a given code C says that if you sort of list all the so this is not a very efficient list way to do this, but the idea is that if there's a unique y prime, so remember, so that you want to think about this in terms of Yolanda. Think this is Yolanda receives y, capital Y, wants to fix it. Wants to fix it to y prime. Okay, and so the idea is that the basic idea of the nearest neighbor error correction method is that if there is exactly one y prime that is closer to y than anything else, then she corrects y to y prime. And there's a sort of border state where if there's more than one vector y prime with a minimum distance from y, then we say that y is detected. There must be some error but it can't be corrected because, well, because we don't know which is more likely to have been an error. So the thing I want to note here, note that the thing about nearest neighbor error correction is that, note, this is a scheme used only in theory. Let's see if I get this widened up. Only in theory, not in practice, because the most naive way to implement this would be to list all possible received words, 2 to the n of them, and list the nearest neighbor of each. So this scheme only exists to show that you can correct errors, a certain number of errors, not a practical way to do so. Okay, and we're 1 minute over, and so I think we'll end there. Thank you very much for being patient and coming in and sharing this time with me and with everybody else in your class. So everybody stay safe, bend the curve, wash your hands and stay home. And I'll talk to you on Wednesday. Bye. See ya.